Hi everyone! Today we're going over Chapter 2 of General Chemistry, which covers the periodic table. Chapter 2.1 says that there are two levels of organization in the periodic table. The first is a group which goes vertically down a periodic table. So this is group 1, and this would be group 2. So what's similar about all the elements in a group is that they have the same valence shell configuration. For example, in group 1, all of these elements have 1 electron in their valence shell, and in group 2, all of these electrons have 2 electrons in the valence shell. The second level of organization is called a period. So this would be a period, and this would also be a period. What the period tells you is the energy level that the valence electrons are at. So hydrogen is in period 1, and so the valence electron of hydrogen is in the energy level n equals 1. And lithium and beryllium are in the second period, so their valence electrons would be in the energy level n equals 2. There are two different types of elements. One is called the representative elements, and the other is called the non-representative elements. So group 1 and 2, as well as 13 to 18, are known as the representative elements. And so this means that the behavior of these groups can be predicted based off of where they are on the periodic table. So for example, sodium and potassium can both react with chlorine to form a salt. And this is very predictable because sodium and potassium have the same number of valence electrons, and chlorine would behave fairly similarly in a reaction to bromine because they have similar amounts. They have the same amount of valence electrons. However, the non-representative elements are all of the transition metals and the lanthanides and actinides. And this is because the transition metals are more fluid in the amount of valence electrons they can have. So you can't necessarily say that two transition metals in the same group will react similarly. Chapter 2.2 talks about the characteristics of three broad groups of elements. The first are the metals, which are shown in yellow on this periodic table to the right, and metals are lustrous, which means that they're shiny. They're malleable, which means they can be hammered or pulled into different shapes, and they're ductile, which means they conduct electricity well. All of these characteristics are because metals have multiple stable oxidation states, which means a metal can exist as a +1 ion, +2, +3, and so on, depending on the specific metal. Some metals can have up to 7 different stable oxidation states, which means they're very flexible in how many electrons they can give up or receive. So this characteristic makes metals malleable because metals are considered to be swimming in a sea of electrons, as in if you have a lump of metal, all of the metals are sharing all of the electrons together. So the bonds are not as rigid, and therefore they can slide past each other in this sea of electrons. This also makes metals ductile because the electrons are free to move around, and therefore they're free to conduct throughout a thin wire of metal. Metals have low electronegativity, which means that they don't like to receive electrons as much as they like to give up electrons. So you'll more frequently see metals in the positive form, as in you'll see them as a cation, and almost never as an anion. Nonmetals are shown in blue on this periodic table, and nonmetals have high ionization energy, which means that it takes a lot of energy to pull an electron off of a nonmetal. They have high electron affinity, which means they're very likely to grab an electron from a metal, and they have very high electronegativity, which means that in a covalent bond, nonmetals are more likely to be hogging the electrons more of the time than a metal would. Nonmetals are brittle, so nonmetals tend to form covalent bonds, and therefore their bonds are very much locked into a specific angle, so they're not malleable, and if you try to hammer a nonmetal compound, it would most likely crack. Nonmetals are also poor conductors because they're not swimming in a sea of electrons. They have very defined bonds, and therefore electricity doesn't really pass through them easily. Metalloids or semimetals are shown in green. And so an easy way to remember where the semimetals are and where the metals and nonmetals separate is with the staircase rule. So if you draw a staircase on the periodic table here, all of the elements that touch this staircase are semimetals, with the exception of aluminum. And it's easy to remember aluminum as an exception because we know aluminum as a very common metal. So metalloids, it's harder to predict the characteristics of metalloids. Some metalloids share more non-metal characteristics and some metalloids share more metal characteristics. But in general, the characteristics of semimetals are somewhere in between that of metals and nonmetals. Chapter 2.3 talks about some of the trends that can be found on the periodic table and goes more into depth on the characteristics that we discussed in the last slide. So first we have to define a term called the effective nuclear charge, which is denoted as Z sub EFF. And the effective nuclear charge is basically the amount of attraction that the valence electrons of an atom feels. So I have two elements here as examples. I have lithium and beryllium, and they're in group 1 and 2 respectively. So lithium is the third element, which means that it has 3 electrons and it has a nucleus with 3 protons, giving it a charge of positive 3. So with this charge of positive 3, there are 2 electrons in the first shell, which means that this first shell has a charge of negative 2. So if you look at the valence electron, you take the number positive 3 and you subtract 2, because these 2 electrons are effectively shielding the valence electron from the positive 3 charge of the nucleus. So lithium has a effective nuclear charge of positive 1, which is the charge that this electron here would feel. So beryllium is the fourth element, having 4 electrons and 4 protons. So these 2 electrons would shield the 2 valence electrons, giving the effective nuclear charge of positive 2. So these 2 electrons would feel a positive charge of positive 2. So the effective nuclear charge increases from left to right in a period. And you can see why that is here, because from left to right, all of these elements are at the same energy level, or they're at the same shell. So as you go from left to right on the periodic table, you keep adding electrons in this valence shell here. And the amount of positive charge in the nucleus keeps increasing, but there isn't an increase in shielding because this first energy level only has 2 electrons and more electrons cannot be added to it. So the effective nuclear charge increases from left to right on the periodic table. Another definition is the noble gas configuration. So the noble gases are this group in blue on this periodic table, and the noble gases are especially stable because the noble gases have all of their shells filled. So as in, like, the valence shell of the noble gases is completely full, which makes them the most stable. So all of the other elements seek to gain this noble gas configuration. So the first periodic property is atomic radii, and atomic radii decreases from left to right. Atomic radii is how big the electron is. So from here to here, this distance is the atomic radii. So atoms get smaller as you go from left to right. And this is because the effective nuclear charge increases from left to right. So as you know, positive and negative charges attract. So this electron here feels a positive charge of +1. So this electron is only vaguely attracted to the nucleus. Beryllium, on the other hand, has an effective nuclear charge of +2. So these valence electrons are more attracted to the nucleus, which means they come closer to the nucleus, giving it a smaller atomic radii. Atomic radii increases from top to bottom, so it increases down a period. And this is because as you go down a period, you increase in the principal energy level, or you increase in the number of shells you have. So if you have electrons in outer shells, this makes the radius larger and it makes the atom larger. And in addition, when you have more electrons, the electrons will repulse each other. And so when the electrons repulse each other, the only way they can go is out. On the other hand, ionic radii, which is the radius of an atom if it became an ion, is slightly more complicated because the effective nuclear charge is the same. For example, if I removed this electron here, this electron would still feel an effective nuclear charge of +2. However, there are now less valence electrons, so there is less repulsion. So cations get smaller, and when you remove electrons from a valence shell, the atom gets smaller. However, if you have an anion, which means if you add an electron here, the effective nuclear charge is still +2. However, there's more repulsion now. So the atom gets larger as the electrons move out to try to get further away from each other. The next periodic property is ionization energy. Ionization energy is how hard it is to remove an electron from its valence shell. So this property increases from left to right, and this is also because of the effective nuclear charge. So for example, lithium has an effective nuclear charge of +1, which is not very strong, and fluorine has an effective nuclear charge of +7, which is really strong, which means that the valence electrons in fluorine are feeling a strong attractive force from the nucleus, so you'll need to add a lot of energy in order to remove an electron from fluorine. On the other hand, the valence electrons of lithium doesn't feel nearly as much attraction, so it's much easier to remove a valence electron from lithium. And another reason why it's easy to remove valence electrons from lithium is because if you remove one electron, lithium becomes the electronic configuration of helium, which is a noble gas and it's very stable. So lithium actually wants to have an electron removed so it can become the stable noble gas form. And this is also true for sodium and potassium, which is why lithium tends to exist as lithium +1 and sodium tends to exist as sodium +1, and magnesium tends to exist as Mg+2. Because if you remove 2 electrons, magnesium becomes the electronic configuration of neon, which is very stable. So this trend of ionization energy also decreases going down, because as you go down, the valence electrons get further and further away from the nucleus. So if the valence electrons are further away, they feel less of an attractive force, and so it's easier to remove them. The next periodic property is electron affinity. An electron affinity is defined as the energy released when an electron is added to an atom. And this increases from left to right because of the same reason, because of effective nuclear charge and because the noble gas configuration is most stable. So using the example of lithium again, lithium doesn't want to gain an electron, because if lithium gained an electron, it would get further away from its most stable noble gas configuration. But fluorine, on the other hand, not only does it have a +7 effective nuclear charge, which is already very attractive to an electron, fluorine, if it gained an electron, would become the electronic configuration of neon. So a lot of energy is released when fluorine gains an electron, and lithium doesn't want to gain an electron. The next periodic trend is electronegativity, which is basically how much an atom likes to hang on to shared electrons when it's in a bond. So, for example, if sodium was bound with chlorine, as in sodium chloride, sodium is not very electronegative. Sodium is actually electropositive, which means it likes to give up its electron because it wants to become neon, and chlorine is very electronegative because it wants to become argon. So, because chlorine is far more electronegative than sodium is, these electrons actually all go to chlorine. So this becomes Na+ and Cl-, and this is an ionic bond because chlorine is just that much more electronegative than sodium is. And for example, if chlorine was bound to carbon, this would form a covalent bond because the electronegativities of chlorine and carbon are not that different from each other. But however, in this bond, the electrons are shared unequally, as in chlorine has the electrons closer to itself and further away from carbon, because chlorine is more electronegative. And so this notation here is how you denote electronegativity. This arrow means that carbon would have more of a positive charge because the electrons are being pulled away from carbon, and chlorine would have more of a negative charge because the electrons are pulled toward chlorine. And so this is basically the same trend as electron affinity. These are just different definitions because electron affinity is when you add an electron, and electronegativity is when two elements are bound to each other. Chapter 2.4 is about the chemistry of different groups on the periodic table. And as you remember from before, a group is defined as going up and down vertically on the periodic table. And the first group are the alkali metals, which are group 1, and it's this group here. So alkali metals are known for having low density, and this is because they have a low effective nuclear charge, which gives them a large atomic radius. So this large atomic radius means that their mass is spread out over a large area, which gives them a low density. Alkali metals easily lose one electron, because if they lose one electron, they can become their respective noble gas form. So sodium likes to give up one electron to become the electron configuration of neon, and potassium likes to give up an electron to become potassium plus 1, sodium plus 1, because the noble gas configuration is the most stable configuration possible. And so you'll rarely ever see these alkali metals in their elemental form. You'll see them as +1 ions. And this is why they're known as active metals, because in their elemental form, they're very reactive and like to lose an electron. Group 2 are the alkaline earth metals. And alkaline earth metals easily form what are known as divalent cations, which just means they have a +2 charge. So calcium likes to form calcium +2, and beryllium likes to form beryllium +2. Because when they form these ions, they can become their respective noble gas forms. And so these are also known as active metals. So we're going to skip a bunch of groups here for later and talk about the chalcogens. So chalcogens have 6 valence electrons. The chalcogens are this group here, which includes oxygen. And they have 6 valence electrons, and they have a small atomic radius because they're toward the right side of the periodic table, giving them a high effective nuclear charge, which means the valence electrons are pulled in very closely. So the chalcogens include some nonmetals, some metalloids, and some post-transition metals, which just means that they're metals, but they're past the transition metals. The transition metals are the orange elements here. So the chalcogens include oxygen and sulfur, which are very, very biologically important elements. Like you see oxygen everywhere in biology, and sulfur is very common as well. The next group are the halogens. And the halogens are this group here. They're group number 7. And halogens are known for being very electronegative because, first of all, they have a very high effective nuclear charge. And also, if they gained an electron, they would be at their noble gas configuration, which is very stable. So halogens tend to exist in either their diatomic form, which means that two halogens are bound together, or in their ionic form, which means that an electron has been added to it. So the next group are the noble gases, and the noble gases are very inert, which means they're unreactive. And this is because the noble gases are already in the most stable possible conformation, and they don't want to do anything to change that. So noble gases have very low boiling points, because noble gases are not really likely to interact with anything else, so they disperse and become gases at room temperature, which is why they're known as the noble gases. Last but not least, the transition metals. The transition metals are all of the elements in orange here, and because they're metals, they have very low electron affinity, which means that they don't like to gain electrons. And the transition metals have multiple oxidation states possible. So, for example, manganese here can exist in either its +2 form or +3 or +4 or +6 or +7. And all of these oxidation states are stable for manganese. So you can find manganese in the wild in any of these oxidation states, but these transition metals almost never become their negative form. So you will never see a negative form of manganese because they have low electron affinity. And as always, thank you so much for watching, and I hope you enjoyed this video.